So today we're going to talk about rational expressions. So working with rational expressions, let's see what we can come up with here. Okay. So the key idea of this assignment will be to simplify or reduce rational expressions by using factoring strategies. Also later on, we're going to try to develop a strategy to find the least common multiple, which we'll use this phrase LCM for that. And we'll kind of work with what we call monomials and polynomials in doing that. Remember, rational expressions will take on the look of fractions. So we have these numerators, and of course we have these denominators. One of the strategies to this is going to be working with what we did last time, which is some of the factoring stuff. So one of the things we've talked about last time is when the factors of the numerator and the denominator are the same, they can be divided out. And sometimes we use this phrase canceled. Remember, we use a lot of these little slashes canceling out. But remember, when we cancel out, remember if the numerator and denominator are the same exact expression, they can actually be divided out. So if I want to reduce 12/18ths, or yeah, 12/18ths, what I'm looking for is a greatest common factor if possible. So one way is if you recognize that 6 is the greatest common factor, you can rewrite 12 as 6 times 2 and 18 as 6 times 3. And you can cancel out the like factor. And therefore, we end up with this 2/3. Another way to do it is we can rewrite using a prime factorization. So remember, if I have a 12 and 18, I can use big T as an organizer. So if I use prime numbers, remember that's that 2, 3, 5, 7, 11. So if I start with that 2, 2 does go into 12 6 times, 2 does go into 6 3 times, and 3 goes into 3 1 time. So we're actually factoring it back into a multiplication problem. 18 would be 2 goes 18 9 times, and 3 would actually go into 9 3 times, and 3 would go into 3 1 time. So if I'm using a factorization, I could change 12 to 2 times 2 times 3, and I could change 18 to 2 times 3 times 3. And reducing basically means if I have the same factor on the top and bottom, we can cancel it out. So if we look through there, we kind of see that we can cancel this 2 with this 2, we can cancel this 3 with this 3, and then the remaining factors would be our reduced form, which would be then this 2/3. So that's using what we call a prime factorization strategy. So if you know what the GCF is, you're done. If not, a prime factorization could also be very helpful. Something else we want to mention is in working with monomials with exponents, the exponents can actually be subtracted if the bases are the same. Notice how if we have x to the 5th divided by x squared, I can see this as x times x times x times x times x times x, because that exponent means there's 5 x's on the top multiplied together, and x squared means there's 2 x's multiplied together on the bottom. And notice how we can cancel out 2 on the top and the bottom. In other words, we're taking away 2. So what we pick up on is if the bases are the same, we actually could just subtract the exponents. So I could say the answer is x to the 5 minus 2, or we could say that's x to the 3rd power. So when I have this x to the 9th divided by x to the 4th, I can just subtract those exponents. So 9 minus 4, notice how there would be a 5 left up here, and therefore the answer would be x to the 5th. Notice here though, when I do my subtraction, 5 minus 3, there's actually 2 left on the bottom. So notice how that would be actually 1 over x squared as an answer. So I have problems like this, and I want to reduce. If you can see that between a 6 and a 12, the GCF is a 6, then you can go ahead and divide that out. So I can mark out the 6 and put a 1, and 6 goes into 12 twice. Notice how here the bases are the same, so I could go 4 minus 2. So these go away, and I'm left with 2 on the top. So if I can figure out what I have, I see I still have 2 x's on the top. So I have x squared on the top. On the bottom, all I really see is this negative and this 2. Typically, we don't leave negatives on the denominator, so I usually put them on the top and just keep the 2 on the bottom. So either out in front or on the top is the best place to put the negative. Usually we don't leave it in the denominator. So if I have an expression like 2 times r minus 4 over r minus 2, notice how we could see that there's a GCF in the top 2. Notice that 2 times r and 4 have a 2 in common. So I actually can factor that 2 out. That's going to leave me this 2r minus 2. That's not right, is it? Let's erase that. So if I do that again, I took that 2 out. So if I took that 2 out, I should be just left with an r, and if I take a 2 out of that 4, I should be left with a 2. So remember, when I take out here, I'm using division. So 2r divided by 2, the 2's divide out, and I'm left with the r, and 4 divided by 2 just leaves me that 2. On the bottom, r minus 2 is not factorable, so we just leave it as r minus 2. And so what we pick up on is, in reducing, if I have the same factor on the top and bottom, I can cancel it out. So since I have an r minus 2 here and an r minus 2 there, I'm allowed to divide those out. That turns into a 1, which we can just drop. And that leaves me basically a 2 over a 1, or we just call that 2. So if I have this expression x to the 4th minus 3x squared minus 12, the top is not factorable, but on the bottom, if you notice, there is a GCF in common there. Again, if you want, you can use big T and see the factor pairs. So I have x minus 4, and on the bottom, notice how they have a 3 and an x in common, so I can actually factor that 3 and x out. And when I pull that 3x out, that leaves me just 1x there. If I pull that 3 and x out of this, that just leaves me a minus 4. So I have this x minus 4 over 3x minus 4. So notice I just have the x minus 4 as a factor on the top. And the bottom actually has 3 different factors, because remember, factors are connected by multiplication. So 3 is a factor, x is a factor, and x minus 4 is a factor. But they do have a common factor on the top and bottom, so we're allowed to divide out those x minus 4s. That leaves me the remaining factors. So since the top divided out, that just leaves me a 1 up there. And on the bottom, we just have that 3x. So 1 over 3x becomes my reduced form of that. So if I want to reduce v minus 5 over v squared minus 10v plus 25, for me, the top again is not factorable, but that trinomial on the bottom, I would probably like to just use the FOIL method. So all I really have to pay attention to, since the coefficient of the first term is 1, all I really got to do is focus on that 25. So the factors of 25 is what we're trying to focus on there. So let me see if I get this where I can see it. Yeah, there we go. So I have a 25, and I have to add to get this negative 10. So when it's in a trinomial form, quadratic term, linear term, and constant, all you have to do is focus on the factors of the constant, which is this 25. But remember, they have to add equal the coefficient of this negative 10. And that's where I use, big T and just put the negative 10 out there because I have to pass both of those. Notice there's not many factors of 25. You know, I could do the 1 and 25, and then the other one is just the 5 and the 5. But since I need a negative here and I need a positive here, they both have to be negative. That's going to lead me to the -5 and the -5. So the way I would factor this then is, you know, the v minus 5 would stay the same. Let me fix that. So v minus 5 doesn't change. But notice how this trinomial will factor into v minus 5 times v minus 5. Because this -5 and this -5 will multiply to give you this 25. And the -5 at v and the -5v does give you this -10v. So that does play out correctly. So now the numerator and denominator are factored. I look for any like factors, and since the v minus 5 is the same on the top and the bottom, I'm allowed to divide those out. So what this leaves me then is nothing on the top. So in other words, it's a 1, because remember, special 1. And that leaves me then this v minus 5. You could also recognize this is a perfect square trinomial. So when I have this b to the third plus 3b minus 28, that looks factorable. So remember, we focus on the factors of the -28, the factors of the constant, but they have to add up to give me that linear coefficient of that 3. And again, I like to use big T as an organizer for that -28. But remember, I have to get this positive 3 here. So we have this 1 and this 28. We have 2 and 14, actually. 3 is not going to happen. 4 and 7. And I think, 5 is not going to work. 6 is not going to work. 7 and 4, that's just repeating. But notice how I need a -28. So one of these has got to be negative. But the key is the coefficient's got to be 3. So I need to get a 3 here. So what we pick up on then is they both have to be, not one of them has to be negative, and since I need a positive 3, the left side has to be negative. And if we notice there, that -4 and this 3, I'm sorry, this -4 and this 7 does add up to give me this 3. So there's my winner. So the numerator will factor into b minus 4 and b plus 7. If I can read my writing there, yeah. On the bottom, I recognize that as a difference of squares. The b is a perfect square and 49 is 7 squared. So I could change that to b minus 7 times b plus 7. But remember, it's also, it's the coefficients. I mean, the constant is this -49. And remember, the linear term is not there, so its coefficient would have been that 0. So notice that if I was using big T, the -49, notice that a -7 and a +7 would have gave me that -49, and they do add it to give me 0. So it also could have just used the full technique as well. So if I look at 6x cubed plus 42x squared, the 42 looks a little more complicated. So what I'm going to do is just identify the factor pairs of 42. The 6 is not that hard. So if I do that 42, I see that we have a 1 and a 42, a 2 and a 21, a 3 and a, what is that, 14? Yeah. 4 is not working, 5 is not working, 6 is, 6 and 7. 7 and 6 is out. That's repeating. So those are the different factors of 42. And notice the strategy really is just the GCF strategy. Notice how they have a 6 in common because there's that 6 there. So what I can do is factor out a 6, and how many x's do they have in common would be 2. So the numerator I can factor out a 6 and 2 x's, or in other words, an x squared. If I do that, if I pull the 6 out and 2 x's, that leaves me an x. If I pull the 6 out of the 42, that's going to leave me this 7. And since I brought out both x's, the inside is just going to be x plus 7. On the bottom, again, I see a GCF to start with. Notice each term is even. Since each term is even, I can factor out a 2. So I'm going to probably have to do this over here on the side a little bit too, and then I'm going to have this x squared, and then it's 13x, and this take a 2 out of that 84 would leave me at 42. So the 2 came out, but notice how we have a trinomial that's factorable. And since the coefficient of the quadratic term is 1, all I really got to do is factors on the factors of 42 that give me a 13. Well, I've already factored the 42 down, and we see that the 6 and 7 would be perfect for that too. So I can factor this in 2 times x plus 6 and this x plus 7. That would be my denominator strategy. So the denominator over here, and that's where it's hardest to keep your work organized. So I have a 2, and I have an x plus 6, and I have x plus 7. What jumps out to me to start with is the x plus 7s cancel out. The x plus 6, I don't see one on the top. This x squared, I don't see any x's down here. I see 2 x's, but I don't see any x's. Now the 6 and the 2, notice the 6 actually is made up of some factors as well. It's made up of a 2 and a 3. So I can actually divide out a 2 here and a 2 there. By doing so, what that's going to leave me then is a 3 up here and nothing down there. That's gone. So what I got to do now is figure out where the heck am I going to write this answer at? So I'm going to try to slide it right here. Notice how I have a 3 left over and then the next squared left over in the top. On the bottom, we just have that x plus 6. So those would be our final answer. Because remember, x plus 6 is a factor. The only way to cancel out an x plus 6 is to have an x plus 6 on the top. So we can't do that. So that is as far as that goes. So 3x squared over x plus 6. On this one, you may see this in your homework is where you have an x minus 3 over 3 minus x. It looks like these would be the same except the signs are backwards. This is a positive x and this is a negative x. This is a negative 3 and this is positive 3. Since the signs are backwards, what we can sometimes do is just factor out a negative. And since this one's kind of backwards, because I usually like to have the degrees the other way around, so notice how we could have x minus 3 on the top, and I could have this negative x plus 3 on the bottom, like so. But notice how the signs are backwards, so I can keep the x minus 3 on the top. And what I'm allowed to do on the bottom is go ahead and factor a negative out. In doing so, this becomes an x, and this plus 3 becomes then that minus 3. If you recall, we did a little bit of that in our factoring earlier with grouping. So notice how this x minus 3 will divide out. So now we have to figure out what's happening. But remember, if you have the same thing on top and bottom, what that turns into is a 1. And since there's still a negative in the problem, that turns into a negative 1. So the next thing we want to get into is what we call the least common multiple. So in the least common multiple, LCM, first off, we have to understand what a multiple is. Multiples of a number are created by multiplying the number by 1, 2, 3, 4, or 5. So the multiples of 25 would be, 25 times 1 would be 25. 25 times 2 would be 50. We would have 75, 100, 125. And they would just keep on going. So 125. Let me fix that. That's just a little too messy. My eyes are getting ahead of myself. So 125. And again, they would just be going on and on. The multiples of 15 would be, 15 times 1 is 15. We'd have 30, 45, 60, 75, so forth and so on. Now, the least common multiple is the smallest multiple in common. So if I look at the multiples, we can see that the smallest multiple in common would be the 75. So the least common multiple would be 75. Now, we also can do this by actually using some strategies in algebra. So we can use what we call a prime factorization. And the least common multiple, it must contain both of the original numbers. It must contain both of the original numbers. And we want to use the fewest factors possible. So again, if we do a prime factorization, we have a 2, a 3, a 5, a 7, and 11. But notice that, on a 25, we already recognize that a 5 and a 5 would make a 25. For 15, a 3 and a 5 would make that 15. So basically, 25 is made up of two 5s. 15 is made up of a 3 and a 5. So the least common multiple must contain these different factors. So I can write down the 5 squared to start with. It needs two 5s. And we also need, here, I already got enough 5. I got more than enough 5s over here because remember, we're using the fewest number possible. I don't need to add another 5 because this has more than enough. So notice how this 5 squared has the higher exponent. I use that 5 here. We don't use this 5 here. Notice here we do need a 3 though. So we need at least one 3 there. So what we basically are doing is we identify the different factors, but what we want is the fewest factors possible. But where that comes from is you actually need the most of each factor in each one. So since there's two 5s here and one 5 here, I need at least two 5s, so that's why that 5 squared came in. Notice how I have a 3 and a 5. The most 3s I see is that 3, so I put that down. And notice that 5 squared would be 25, and 25 times 3 would be 75. What I also like to do is I just like to build it. If I start with the first one, 5 squared, so if I have 5 squared, and then when I look at the next one, I only add 2 what I need. And since I already see a 5 here, I don't need that, but I still need a 3, and I still get to the same spot. So what you should see here is you should see both factors present with the fewest factors possible. So for 25, I do see a 25 because there's a 5 times a 5 there. For a 15, I need to see a 3 and a 5, and I do see a 3 and a 5 with an extra 5 left over. So we just don't need that. And so therefore, if we multiply that all out, we would still get the 75 as our GCF. So if I want to find the least common multiple of x to the fourth minus 9x squared and x squared minus 3x, what we do is we need to factor each one. So I have this x squared is my GCF to start with. When I pull that x squared out, that leaves me x squared here. And if I pull that x squared out there, that leaves me a minus 9. But notice x squared minus 9 is a difference of squares. 3 squared gives me 9. So I can write that as x minus 3 times x plus 3. So this has two x's, 1x minus 3 and 1x plus 3. So it has three different factors where the x is repeated twice. Over here we have an x and we have a x minus 3 if I pull out x as the GCF. So this has an x and an x minus 3. So when I do my GCF, you have to have an x, you have to have an x minus 3, and you have to have an x plus 3. Those are the different factors. But how many x's do we need? I need at least 2 to make that. So I need to put an x squared there. How many x minus 3's? This only needs 1, this only needs 1, so we got more than enough there. X plus 3, we got our x plus 3 there. So that would be our answer, just pulling that all out. What you also could do is just write down the original expression in factored form, x squared minus x minus 3, x plus 3. So I can write that down. And this one needs an x, but notice how we got more than enough x's there. This needs an x minus 3, and we are having x minus 3 there. So we're good to go. And again, when you do the LCM this way, you actually don't have to multiply back out. You can just leave it in that form. Now this one in your notes is different, so you'll probably have to rewrite this one in your guided notes. So I have this trinomial, this binomial, and this monomial, and I'm trying to find the least common multiple of it. So if I look at this, what I see to start with is I see an x squared. So I don't see anything else in common. So that leaves me a 64x squared minus 16x plus 1. Notice how this is a trinomial that's factorable. I'm probably going to use 4 square on that because it has a coefficient in front. This is the long way, but I feel more comfortable with it sometimes. So the leading coefficient goes here, the 64x squared. And remember, when you do scratch work, it's kind of be off to the side. 1 is my constant. Now remember, when I do big T, you got to multiply the leading coefficient to the 1. So 64 times 1 is still 64. What you have to add, though, is you have to add to get the linear coefficient, which is that negative 16. So I need a 64 and a negative 16. So the factors of 64, 1 and 64, 2 and 32. 3, yeah, no, 3 doesn't work actually. 4, yeah, 4 and 16. Yeah, that's 64. 5 doesn't work. 6 doesn't work. 7, nope. 8 times 8 does give me 64. Notice that I need a negative 16. So these guys here would be perfect. That negative 8 and negative 8. Because a negative and a negative make it positive, and a negative, when you add them, give me that negative 16. So I'm going to rewrite the middle terms, the linear terms, using those negative 8x's. Here, the GCF is all you got to pull out, and notice that we recognize that 64 does have these 8's in it. So I can pull out an 8 and an x as a common factor. And we know that 8x times 8x is actually going to give me this 64x squared. Here I would need a negative 1. 8x times negative 1 is negative 8x. Here I would need a negative 1 as well. Negative 1 times 8x is negative 8x. And negative 1 times negative 1 is positive 1. So this actually factors into x squared, and I have 8x minus 1 twice. If I factor this one out, I have an x to the third comes out, and I have an 8x minus 1. And x to the fourth is just an x to the fourth. So if I'm doing the LCM, all you have to do is really identify the different factors. So I see x's, and I see 8x minus 1's. Those are my different factors that I see. Now, the most x's I see is I actually need 4x's, so I need at least 4 x's there. 8x minus 1, this has 2, so I need at least 2 to make that. So x to the 4 times 8x minus 1 squared would be my LCM. Now, again, you could just write the original one down, and notice that the x to the third and x to the fourth, I would still need 4 x's altogether to make that last one. So what you're trying to do is see this in the fewest factors possible, and that would be it. Okay, so that's a tough question. Another thing we want to talk about is division by 0. Notice that when the denominator is equal to 0, this is called division by 0. So in division, if you recall, it's you basically do it by thinking backwards. So instead of saying 12 divided by 2 is something, you can go backwards and say something times 2 must get you back to the 12. So what times 2 would give you 12? Well, that would have to be 6. So what we're looking for would be the 6. Now here, notice when you have that 0 in the denominator, something times 0 must give you 5. So something times 0 must give you this 5. Well, remember the multiplication property 0 says if you multiply by 0, you will never get 5. So what we pick up on is, on this is going to be not possible. You cannot multiply a number by 0 and get 5. So what we pick up on is a special little thing here. Division by 0 is not going to be possible, so we use the words undefined there. And so undefined means there's not going to be an answer. No answer can be given. So that's kind of important there. So in summary, We talked about rational expressions may need to be reduced. Notice how we use factoring and canceling. So again, you may have to review your factoring strategies as necessary. The more factoring we do, the more comfortable you will get with it. And the LCM, remember, it's the smallest multiple between the given expressions. So factoring can be used. And remember, the answer must contain the original expression using the fewest factors. And so there's a couple of ways of doing that. So that concludes this lesson. So y'all have a good day.